who is Ramesh Mainali, who's going to tell us about gravitationally lensed Z2 reionization-era analogues and implications for carbon-3 detections at Z greater than 6. So Ramesh, you can go ahead and start sharing your screen. And
okay, can you hear me?
Yes, go ahead.
Okay, great, thanks. Okay, hello everyone. I'm Ramesh Mainali, currently a postdoc at NASA Goddard Center. First of all, I would like to thank the organizing committee for providing me this opportunity to talk about my research. Today, I'm going to talk about some of my recent work on the study of gravitational-lensed Reionization-Era galaxies. This work has recently been published and available on arXiv. Now, to begin with, here I show a few spectra of Reionization-Era galaxies showing detection of strong carbon-3 emission at redshift greater than 6. Since past few years, we have been finding these exciting carbon-3 features among redshift greater than 6 galaxies, which has never been found in star-forming galaxies at lower redshifts. Understanding these features is particularly important in context of OIII galaxies and their role in reionization. While the present sample is still small, we find that about 14% of redshift greater than 7 galaxies show intense carbon-3 with equivalent width greater than 20 angstrom. So how does this compare to low redshift sample? Well, in a survey of 184 star-forming galaxies targeted at redshift of around 1, none were found with carbon-3 above equivalent width of 20 angstrom. This suggests that intense carbon-3 is more common at redshift greater than 6 than at lower redshifts. Now, in order to understand the carbon-3 emissions we are finding at redshift greater than 6, it is important to explain origins of these lines, which is currently unclear. We currently don't know whether massive hot stars are powering these lines or AGN are required to explain these features. Now, in part, this problem arises because some photoionization models struggle to produce these intense carbon-3 emission with equivalent width reaching above 20 angstrom using only hot stars model. And the only way we get above 20 angstrom carbon-3 emission is using AGN models. If this is the case, it would imply that the population of carbon-3 emitters we are finding at redshift greater than 7 are actually AGN population. Currently, it is extremely difficult to tackle this issue at redshift greater than 6. However, it might help if we can find similar sources at a lower redshift where more detailed study is possible. In the literature, we find that that equivalent width greater than 20 angstrom carbon-3 detections are mostly associated with AGNs. Among star-forming galaxies, we find that carbon-3 equivalent width increases with oxygen-3 equivalent width, as shown in figure. However, current survey have yet to find sources with carbon-3 equivalent width as strong as those observed at redshift greater than 6. In part, this may be because very few objects with oxygen-3 and s-beta equivalent width reaching around 2000 angstrom have been targeted in surveys. Now, in order to answer some of these questions, we recently initiated a spectroscopic campaign aimed at targeting extreme emission line galaxies at redshift of around 2 in Hubble clusters, especially from a program called RELIX, where we looked for carbon-3 emission among sources with oxygen-3 plus and s-beta equivalent width reaching as large as 2000 angstrom. Now, by targeting gravitational-lensed galaxies, we are basically selecting dwarf systems that likely have lower gas and stellar metallicity, both of which may enhance production of carbon-3 line. By selecting photometric axis objects with oxygen-3 and s-beta equivalent with reaching up to 2000 angstrom, we are selecting systems likely dominated by hot younger stars that appear after a burst of recent star formation. So the question is, do these systems tend to show more intense carbon-free emission? So here are the spectra of the objects from our sample showing detection of strong carbon-free line. In some of these sources, we find carbon-free equivalent with as large as those detected at redshift greater than 6, reaching beyond 20 angstrom. At this redshift, combined optical and UV spectroscopy provides insight into physical conditions of these systems. Okay. So first thing we can look into is the source of intense carbon-free with equivalent with beyond 20 angstrom. Using emission line ratios and with the help of diagram like classic BPT diagram as shown in figure, we infer that these systems are most likely low metallicity galaxies dominated by young stellar population. We find no other evidence of Asian activity in this system, yet we are seeing carbon-free equivalent with reaching beyond 20 angstrom. We further use line ratio diagnostics like commonly used O32 and R23 to compare this system with star-forming galaxies at redshift of 0 and redshift of 2. Our analysis suggests that the system is dominated by highly ionized gas as proved by its large O32 value. And using metallicity sensitive blinds, we measured metallicity of around 8% solar metallicity. Now, one may argue that these systems may have enhanced carbon abundance and thus show stronger carbon-free line. However, we measure subsolar carbon to oxygen abundance of about 40% solar value, as expected for similarly metal pore systems. We have further used a photoionization tool called Beagle to model broadband LCD and available emission lines. The modeling further supports that the observed data are better reproduced by young stellar populations of around 3 million years age and require very large ionization parameter and low gas phase metallicity of around 10% solar, which is expected from a dwarf galaxy population that are caught in the midst of large bursts of star formation. Now coming back to this carbon-free versus oxygen-free equivalent with relation, we can now see that strong carbon-free equivalent with reaching beyond 20 angstrom as seen at redshift greater than 6 require very strong oxygen-free and S beta with equivalent with similar to 2000 angstrom. Recent studies have shown that these strong oxygen-free emitters become more common at redshift 7, representing around 20% of the population with largest specific star formation rate undergoing recent burst of star formation. Now there is some scatter in this relation, and if you want to learn more about this scatter and the origin of this scatter, please listen to Meng Tao's talk right after this talk. Now, putting together all these evidences, this suggests that strong carbon-free emission that we are finding at redshift greater than 6 likely reflect evolution of galaxy population from reionization epoch to redshift of around 2. In the reionization epoch, larger fraction of galaxy population likely show larger specific star formation rate and hence strong optical line equivalent with following extreme bursts of star formation. At the same time, earlier galaxies are likely to have lower metallicity compared to lower redshift population. Okay, in summary, I present detection of strong carbon-free emission similar to Reionization-Era galaxies among gravitational-lensed extreme emission line galaxies at redshift of around 2. Our combined analysis using optical and UV lines suggests very low metallicity hot stars are likely powering strong carbon-free lines. This is further supported by our photoionization modeling that reveal young star population of around 3 million year age, high ionization parameter, and low metallicity. Finally, detection of strong carbon-free emitters in the Reionization-Era may reflect population of galaxy with lower metallicity dominated by young stars undergoing recent bursts of star formation. Thank you.
Thank you very much, Ramesh. That was very, very nice. Yes, so let's look at some questions. Do we have any questions for Ramesh? So there's one from Rebecca, Rebecca Bowler. She asks, is there any contribution from AGN, or can the spectra be completely described by star formation?
With our current data, our data is better described by star formation rather than AGN. As I saw in some of this BPT diagram, we can rule out some of AGN contribution using this BPT diagram as a, and also we don't see any any evidence of other AGN like spectral features in our data. And also, these our emission lines are very narrow compared to what we expect from AGN spectra.
Yeah. Tom Toons asks, how do you understand the very young ages of these stars? That is, why are there no slightly older stars with ages 10 to 30 million years, say?
That's a very good question. So basically, with our model, what we are concerning is the recent, star formation or stellar age in recent times. Okay, and we cannot actually rule out contribution of or presence of evolved star in these systems. In fact, if we model our current data with like two component stellar ages older older stellar population on top of recent burst of stellar stars, then we can see that evolved stellar population as well as like around 70 or 80 years cannot be like ruled out with our current data. Yeah.
Okay. Are there any other questions? There's Danielle Scherer mentions, I think this is just a comment more than a question. As a complement to your slides, the VUDS survey has studied large samples of carbon-3 emitters and finds indeed that they're quite rare. Let's see. There's a question from Hakim Atek. How does the carbon-3 versus O3 to O2 relation look like? So O3 over O2 versus carbon-3.
Yeah, so carbon-3 equivalent with tends to increase with oxygen-3 by oxygen-2, O3 to value. Actually, I didn't show that relation in here, but yeah, there is like we find like it is most likely that O3 increases with carbon-3 equivalent with, and in other sense we can also see that there is a direct correlation between carbon-3 equivalent weight versus oxygen-3 equivalent weight, right? And then we also find these strong oxygen-3 emitters with largest equivalent with values. They are tends to they are directly related with O3 values. So yeah, there's like direct relation between carbon-3 equivalent with and O3.
Okay. Well, thank you, Ramesh. That was very, very interesting, and I think